opportunity of being talking to such a nice audience. Second of all, let me just say that what I will talk about is going to work with Nancy and Stefan Mann. So in the back of our mind, we can keep during the entire talk this basic idea that we often hear in our talks and in our seminars, that a skew product with a sufficiently mixing base is the same as a skew product which with the given fiber at a random base. We have heard this statement in many different ways, right? And so the idea of the talk is actually to turn this statement, which is informal and quite suggestive, quite impressionistic, into some qualitative statement which we can fix. So if for you it's obvious what this statement means, then we'll just flow along with the talk. But if you want to know more about me, let me just spell it out. So in general, when we look at a discrete dynamical system, what we have a map F on some space chi, and then we take a point in our phase space, and then we look at the orbit of my point. This is the most basic thing you can do with a dynamical system. You just take a point and follow its orbit. So what we mean by a force, the force dynamics is the one which, is given a family of maps on the same phase space, where omega belongs to some space omega of some bigger space. Then we take a point X and we first apply a map, then we apply a different one. And so on and so forth. So this is what we mean by force dynamics. So this one is just a standard discrete dynamical system, but in this case, at each step, we apply different maps. All of them can be thought as perturbation of one single maps, or they can be thought as a family of maps which have very different properties. We're not saying anything at this stage about the types of maps. So what I want to distinguish here is basically two types of ideas, what we call random forcing. So when I talk about random forcing, what I'm really saying is that my sequences of omega I is chosen, for the infinity, is chosen as an independent, identically distributed sequence. And then when I talk about deterministic forcing, I still have my sequence of omega I, but what happens is that I have a map G which goes from omega to omega, and omega I plus 1 is the map G applied to omega I. So the separation between random forcing and deterministic forcing is not sharp. Of course, you can see one as the other, and in some situations you can see deterministic forcing as random forcing. But in principle, there is a philosophical difference is taking something which is distributed independently and identically and choosing a sequence of it, and instead having a map which generates your maps Wi. So before, in the rest of the talk, what I will try to confront or compare is I will use, as was already said, I will use random forcing as the benchmark for deterministic forcing. So in order to do that, let me first introduce a little bit specify a little bit what random forcing is all about. So when I talk about random forcing, so suppose Xn is a stationary Markov chain. Such that Xn plus 1 is the same as f omega n Xn, and the sequence of omega n is drawn from some distribution mu. Then if X belongs to my space and R is a set, I can say that the probability of starting at the point X and landing in the set A is the same as basically the probability that X1 plus 1 belongs to A in condition on the fact that Xn is equal to X. And since I'm given this mu, it's the same as saying is that is mu of the maps which land me in A. So in principle, what I just want to know, I want to know what are the chances that at a given step I start from X and I land at the set A. And the probability of this conditioned event is the same as, given this assumption, the probability of mu that my family of maps allows me to land in the set A. So with this in mind, is that, of course, instead of, we know that this idea of following one orbit on one point is an ill idea in some sense. So, but once we have this in mind, we can say that for a mu, for a probability measure, then I can define an operator P mu, which is the same as the integral over X over d mu X of my transition probabilities for my sets. And if I do some juggling, it becomes obvious that this is the same as the integral over d mu of omega f of the pullback of mu. So this last formula actually tells me that in the same way as this one did, that basically my operator, the evolution of my measure, of my probability measure, given the operator P, is given by an average of the transfer operator. You can think of this map f omega for the moment as just noise. Picking them up and adding to it some noise. So once we accept the idea that random forcing is just an average in some sense of this map, then we can introduce one of the main tools in this business, which is called geometric ergodicity. So, what is geometric ergodicity, and what properties, what part does it play in these ideas? So, if pk is the case transition probability, and dTV is the total variation distance, the total between probabilities and measures, then we can say that as a definition, a stationary Markov chain is geometrically ergodic if there are c greater than 0, lambda which belongs to 0, 1, such that the total variation distance between the iterates of my transition probabilities are smaller or equal than the constant lambda to the power n for all x1, x2, which belongs to this guy. So what is geometric ergodicity? So geometric ergodicity just means that in some sense, whenever I'm looking at my transition probability and I have a measure, my measure starts to collapse one on top of each other. They start to couple in some sense. As in fact, one can prove that when this definition is satisfied, as consequences, we have that the operator P has a fixed measure, and on top of it, let me write down here. So the total variation distance between the evolution of the measure mu and my fixed point is smaller to equal than c to the lambda n. So the point is that this definition, one can see right away, it's extremely powerful because it tells you that whatever you start, you're going to have things collapsing on top of each other. And so one is wonder, how do we prove such a strong property? How do we prove geometric ergodicity? Well, it is a highly investigated and well-known topic and well-known line of research, and there are many different ways of proving that such a condition is satisfied. I'm just going to give one theorem which is which has been well known for ages, which says that given again xn as a stationary Markov chain, assume that there is a measure M, probability measure M, epsilon greater than 0, and then n0 which belongs to n, such that P n0 of whichever point x and whichever set I chose is greater or equal than epsilon times the measure of my set. Then my chain is geometrically ergodic. So the way I see this statement is that this kind of theorem, which has been known for ages, guarantees that there is some amount of diffusion in my system. Why? Because once I weight n0, whichever are the two sets, there is a small fraction of it which is really overlapping. And if I weight two n0 steps, then there is twice as much mass which is coupled. So the way I'm seeing this result, and this is not the most refined version you can find in these sets of proving geometric ergodicity, is that it guarantees me some kind of diffusion. Let me just mention that This is the result, the way we use it in the theorem, and the conditions we check are checked against this type of theorem. But there are more, there are lots of alternative results. To this kind of theorem, and which are more or less generic, or more or less refined, or more or less suited to any tasks, and they rely on Petit set, for example. And this is the work of mine and Tweedy from '93. Or, for example, they can rely on Lyapunov functions. This is '93. There is some work on Lyapunov's function by Harris in 1965, or this more recent work by Ehrer and Mattingly in 2011. So what I just wanted to say is that this is the version I'm using, but in practice, whenever you want to check or use geometric ergodicity, you have there are a number of alternatives which you can use for your theorem. So this more or less is what I wanted to say about random forcing. The situation is basically contained in this setup. What happens is, as I said again, is that my sequence is chosen random, then my operator P shows my evolution, how my measure evolves with respect to an average, and as a consequence of geometric ergodicity, whenever I can prove it, what happens is that I have a stationary point, and whichever measure I start with, the distance between this measure and my mu zero is shrinking exponentially. Now that I've shown and I discussed how random forcing and what is my benchmark, say, theory, I have to move to the deterministic forcing, which is the part I really would like to study. So, when we study deterministic forcing, what we really mean is that we are studying a skew product from omega times x to omega times x of the form f omega x, which is autonomous in the first coordinate, and in the second coordinate of the fiber depends from the first one. So along the talk, I will use the usual conventional idea that this part is called the base, or the horizontal coordinate, and this part is called the fiber, or the vertical coordinate. And it's obvious to see that this way of looking at deterministic forcing as a skew product has the obvious advantage that if you write the iterate of the map, which is what we do, what we start with in dynamical systems usually, on the first coordinate you just have the iterates of the map G, and on the second coordinate now you have f gn minus 1 omega composed f g omega composed f omega x. I wrote it this way just to show the dependence of this point from the composition of all the maps. Of course, you can rewrite everything in this with this notation, but it becomes slightly more cumbersome. So when we have in this setup, I'm going to state what's so-called, not so-called, but what we all know as a, let me just call it meta-theorem. So what is the general structure of, what can we say about this kind of skew products in general? So in general, so we assume that map G from omega to itself is ergodic with respect ergodic with respect to some measure mean. And then we also ask, in general, that f omega share the whole family of share properties that imply a good spectral picture. So if you look at the literature, all the results most of the results you see on skew products, they do have basically this structure, that you have a map which is ergodic, maybe invertible, maybe not too much ask on it. But then the family of maps f omega shares some properties such that when each one of them might have a very good spectral picture, or they have a very good spectral picture on average. So I'm not going to this is a meta-theorem because I don't want to get into type of system and kind of system, but what happens is that once you're in this setup, then you usually have lots of results, a hierarchy of the result, as we say. So you have stationarity, stationary measures. You have exponential decay of correlation. And if, for example, you have central limit theorem, almost sure invariant principle, and all kinds of results that you would like to think. So this is what has been in the literature, and let me just say that let me just put a few words about the people who worked into this business. So I apologize for all the names I will not mention, but the literature on skew product is extremely vast, and I will use 3 works as references, and if you check the bibliography and the nice literature descriptions in the works, you find most of the literature available. So what happens is that if the f of omega are uniformly expanding, then this work by Body in 09, and there is work by Nicol, Aimino, and Valienti in 2015. If you assume that your f omega satisfy some sort of average or some sort of Lasota York inequality, still with some amount of uniformity, then there is the work by Dragicevic, Froeland, Tocqueville, and Valienti still, 2018. And then there are also some results which I want to mention because they are one of the few results where you assume that f omega are not uniformly hyperbolic. By Bazun was inclusive in 2019. So basically, in this, when you scan this work, you find out that this meta-theorem, once you spell out the properties of the f omega and the g, allows you to obtain this kind of results. Just as a summary, before I move forward, let me just divide the before I introduce directly the assumptions of the set in the setting I'm working with. Let me split into two what we have seen. So in random forcing, you have strong assumptions on the sequence and omega n, and then you have very mild assumptions on the dependence of the map, which sends omega to f omega, and you have almost no or very weak assumptions on the maps on f omega itself. So this is what was on the boards that I raised. Now we have seen that in the deterministic setting, what we do is that we have almost no assumption, very weak assumptions on the sequence, on omega. Oh, sorry. Of course, if I write it this way, it means that I have very weak assumptions on G. On the map G, omega itself. And then I have, again, mild assumptions on how the omega maps into f omega. And then I have, on the other side, very strong hypothesis on the maps f omega, on the fibers themselves. So the theorems that I will show our work have a mixed setups. They have a mixed setup, and they have a different kind of flavor, because we will assume very strong. So it's still deterministic. It's a deterministic process. And then we will ask for very strong assumptions on the maps G. Then here stays the same. We have mild on out map f to omega, and then we will ask basically weak or no assumptions. Very weak assumptions in our fibers. So it's really something in between the two words, because you see, these are what I meant at the beginning when we say that we often say that the maps which is sufficiently mixing in the sufficiently chaotic in the base can be replaced by this analogous random part, and then the two systems should behave the same. So in order to prove this kind of statement, what we can think of these maps, the base map, as having strong assumptions. And what do we mean by strong assumption? As usual, we mean that you can think of these maps as a very strongly expanding maps. So they expand, and they expand extremely fast, like 1000 mod x, so 1000x mod 1. Okay? And so, the result.
So basically this is the same as random, but the emphasis is different.
So it's not the same as random, and you will see.
What you wrote is the same, right?
So
Strong, mild.
no, the problem is that it is the same as this setup,
Yeah.
but the sequence of your maps, it's not given by some random process, but it's given by your map G. Well, you will see that actually it does make a difference, because the point is that in this setup, let me just to go for it. No, it's fine. So let me put in this case, there is no guarantee that you have, for example, an SRB measure. So the fact that itself that you don't have an SRB measure makes even talking about decay and correlation extremely difficult. So this is why actually that's what the result holds. So just for the sake of the presentation at this moment, and before I show you, let's say I discuss the full power of the result, let me just use a simplified setup to state. So to the result, So we assume that my space omega is just the one-dimensional circle, and x is the same. So this is just to say that really my map f omega x is g omega and omega x. And so I ask that g from phi to itself belongs to C2, and there is a sigma greater than 1 such that the derivative of the map, the absolute value, is greater than sigma. And on top of it, I ask that G has bounded distortion. So these are the maps. Bounded distortion means that the second derivative over the square of the first one is bounded by a constant. Bounded by a constant. And as far, sorry? Okay. So this is for the base, right? And on the fiber, I only ask that the map is Lipschitz. So I basically have a very mild regularity requirements, very weak requirements on my fiber. I didn't ask much, I just asked a little bit of regularity. So as a first remark, I just want to say that as a result of the first two hypotheses, from hypothesis on G, what we guaranteed is that there exists mu G a measure which is absolutely continuous with respect to Lebesgue and with density rho G. So just by these two steps, this is what I've guaranteed. So far, this is what I'm assuming, and in this case, obviously, we define the so-called random counterpart. And what do we mean by this expression? If you remember when I discussed random dynamics, I construct an operator P, which was an average version of all my maps with respect to the omegas. So in this case, what happened is that I'm taking the average with respect to the measure mu G of the maps F star omega mu. So it's clear why we can think of this as the random counterpart of our deterministic dynamics, because the fiber is exactly the fiber that I've given, which is just Lipschitz, and here I'm integrating with respect to mu G. This doesn't mean that I'm choosing my sequence at random. My sequence is just given, but I have an invariant measure which allows me to define this integral. So following the scheme which I prepared, which I discussed already, I will assume what I call the working assumption. So those three together, they don't clearly spell out what I'm working with. But remember what I said about geometric codicity? I just say that as a working assumption, there exists a C greater than 0 and a lambda which belongs to 0, 1, such that for all measure mu and nu, which belongs to the probability measure of my torus, then the population distance between P and mu and P and is smaller or equal than C to the power n total variation distance between mu. So remember before that I discussed geometric ergodicity, and I said that there are lots of ways to prove geometric ergodicity. So this statement is the working assumption because it actually says that along with the properties of the map G, what we have to just verify is that my operator P, which is defined as a random counterpart of average, has this kind of property. So it's somehow easy to verify this working assumption in many different cases, and I will discuss it after the theorem. Before I state it, let me just make a few observations and notations. So we let the W be the Wasserstein distance. The Wasserstein distance between measures. And which is weaker than the total variation distance. And we let this operator pi, or we call it V because it's the squashing on the vertical marginal, is just, it takes a measure on my space and squashes it on the vertical component in a way that so that what happens is that the vertical squashing of a measure mu with respect to a set A is basically the entire measure mu on the torus multiplied by H sub. So this is called the vertical marginal. So this measure, which I just wrote here, is called the vertical margin associated to mu, because it's the squashing is how you see your measure when you put it on the second coordinate. So this is what we are really interested in, is the fiber, the dynamics in the fiber. So it makes sense that for us we just look at the second component. Now, given all this, I can finally show the result. And the result goes this way. So, theorem, let F as before. There exists nu bar, which belongs to the measure, which is the probability measure of C tilde greater than 0, lambda tilde, which belongs to 0 and 1, and for all epsilon greater than 0, there exists lambda 0, which depends from epsilon greater than 1, such that if my expansion is greater than lambda 0, then sigma 0, then the vastest distance between the projection of the units of my measure and my stationary measure is smaller or equal than C lambda to the n plus epsilon for all n which belongs to n, and for all measures which belongs to a slightly smaller class than the entire sets of probability measure. Let me just make, since this is the central theorem, let me just make few remarks on what it means and how you use it. So you're given a system which is a very large expansion, or somehow a very large expansion in your fiber are all ellipses. So you give me some sort of epsilon. You give me one epsilon, which you choose. And I'm telling you that I can construct a sigma 0 such that if my expansion of the system is greater than this sigma 0, then my system has an approximate decay of correlation expression. So you need to think of this as the fact that, unluckily, with such mild hypothesis on f of omega, there is no guarantee that there is, as I was saying, an SRB measure or any kind of reference measure that you can really use. You can use eta omega, eta bar, this you can use. This is guaranteed by your geometric ergodicity, but this is not invariant for your Q product itself. It might not be. So let me just say a few more words. So from this expression, you see that the operator P does not depend from the map G itself, but just from its invariant density. And the second thing which I want to say is that we shall put it here on the side. So in this case, for example, the so-called working assumption is guaranteed by asking that the fiber is, for example, C2, and that with C2, the fiber is C2 just with respect to omega, and that the derivative with respect to omega of the function is different from 0. So it's not so difficult to find the weaker condition on which it works, but this, for example, is guaranteed in this situation that this expression will hold. And so there are various things also which I want to add, that in general, the operator P does not preserve these maps, does not preserve this measure. So this measure is, so the measure eta is a fixed point of the operator P, of this operator, of this average operator, only if the map has no distortion at all. Okay? And so it is clear that out of this theorem, as a corollary.
May I ask a question?
Yes, sure.
Where's the sigma going? In the statement of the theorem, there is a sigma 0, such that, and then I see no sigma anymore.
Yes, it is true. Because the point is that is that. Yeah.
Aha.
So what happens is that your map is hidden in this number here, basically, right? So if your maps must be sufficiently, your base must be sufficiently fast mixing for this approximate result to hold. But this, from the physics point of view, is not a big, it's not a really big deal, because what just means is that you need to prepare your system for longer, and you need to iterate your maps longer and longer before you inject it into your Q product. Yeah, you cannot really compose. If you compose a family, you get stuck because you have some displacement and some other quantity which gets. But you can write a map F, which is just an iterate on the first component, and then compose it. And so, let me just say a few other words about it. As a corollary, of course, we get what we call an approximate. I'm sorry that I won't have time to go into the proofs, but let me just give a few hints of what's going on. So first of all, I stated the theorem in the case of one-dimensional dynamics, because both on the fiber so the fiber is one-dimensional and the fiber is two-dimensional and the base is one-dimensional. But in the paper you find the whole result stated for F. Let me just write them in a few marks. let me just make very few quick remarks. So in the statement, in the paper you will find the proofs for f, which goes to time n, pi time n, into whatever dimensions you like. So the proofs require us a very hard and many new ideas to be worked in this way with respect to the one-dimensional case, but they still go through. The second remark which I want to say is that basically, so as a very, just 2 words on the proof, what happened is that in principle, given a measure mu, if mu can be disintegrated in mu omega, then f mu, f star mu can be disintegrated. And out of the fact that you have to disintegrate both this mu and this f star mu, you find that your class of measures which you can deal is slightly smaller than probability measure, and which are those which have some L Lipschitz constant, which is given which you can improve. And as a very, very last remark, I would say that we don't have good estimates in general, but in the very special case of in the very special case of maps with no distortion, we actually have an estimate on what that epsilon and how it relates to all the parameters. So basically, epsilon is more or less the smallest between these two numbers, c lambda to the power n and 2 sigma to the 1 L to the power n. So what happened is that you see what happened? So in this business, you have to guarantee some amount of diffusion, and you have two players into the game. You have, on one side, you have the contraction, which is given by this lambda, which is given by your geometric ergodicity. So this number, this sequence is decreasing. And on the other side, whenever you apply your map, this is diffusion, this number is increasing because it's L to the n, is your Lipschitz constant, which gets stretched. So it's, in some sense, you have to find the balance between the two. And what happens is that in the very simple case of maps with no distortion, this number, one knows that is as small as this one.
So the sequence large enough to get 0?
So it's not like that. It's just what I'm saying is that, so this sequence is decreasing and this sequence is increasing. So there is a minimum point, which is morally when this one is the same as this one. So what happens is that basically your expansion roughly compensate for your Lipschitz constant. And let me just say again, when you have a lot more on your fiber, when your fiber shares some properties, then you have hope to have more precise results. But this is a very weak kind of request which you have on your fibers, and so you're discharging all the difficulty on the fact that your maps are sufficiently fast expanding. And this is actually why the epsilon into this proof can be chosen more or less in this way. So think of it this way again. If you want an epsilon which is very, very small, then you have to increase your expansion by by a relative factor. And again, so maybe it's not what we would like. We would like to have decay of correlation as well, but a complete decay correlation. But this is actually the nature of the result. The result is approximate because the requirement on the fibers are not so much at all. As it doesn't ask too much, we have a family of examples or a family of systems which we can conjugate it to this. to actually which we can apply this result. And in general, it's quite nice that you can weaken your expectation from exponential decay correlation to this approximate one. Also because when you simulate something on a computer or when you look at physical experiments and you truncate at finite time, you always have an error which comes from your truncation. And so if the error is comparable to what the theorem gives you, you can just forget about it and say that you observed exponential decay. And that's all I want to say.
Any questions for Paolo?
So in this general statement, do you also assume that the map is expanding, that it has or can you allow, like, for instance, a dose of diffeomorphism or something like that?
So you replace, in this general setting, you have to replace both this one and this one. But the replacement is straightforward because you control the differential of your G. And you ask that in some norm is greater some amount. And instead of asking that this is a Lipschitz with respect to one coordinate, you just take the family of coordinates you are considering. So, but you have to, there are analogous, also bounded distortion, there are analogous statement which involves differential. So you can.
But if you assume that G is anosoph, for instance, this should not expect this to hold.
Is G expanding?
Yes, Gx is expanding. Yeah. So if you're an anosoph, you have a part which is contracting, which actually messes you up. It's a very different kind of situation. Also, in the case where your map is anosoph, is exactly what I was saying before, because that is the kind of setup which you can and you should use more precise kind of tools. Those relied on the spectral, on the transfer operator in another sense, because you have finer properties of your system.
No, it was the same question.
Okay. No more questions? Okay. Thank Paolo.